Good morning, everyone. My name is Yukun, and the title of my presentation today is FPGA implementation for rapid prototyping of high-performance voltage source inverters. So now here's the outline of this presentation. And first, let's look at the introduction. So with the wider adoption of wide bandgap power semiconductor devices like silicon carbide and the gallium nitride, the switching frequency is ever increasing. Higher switching frequency can reduce the size of passive components and increase control bandwidth. However, the performance of traditional digital platform like DSP or MCU would be the bottleneck when trying to increase the control bandwidth, especially for more complex systems. FPGA could be a more powerful alternative, but the long development process with traditional design methodology makes it difficult to be adopted. This seminar introduces an FPGA design methodology with low development time and effort targeted for rapid prototyping of high-performance power converters. So now let's look at the selection of our platform. So here are some typical types of FPGA-based digital real-time system. So first, we have a type 1 pure FPGA architecture, which has a very simple one-chip solution and with highly customizable hardware. But the lack of peripherals like ADC, DAC, or Ethernet communication, and the requirement for RTL design only would be the disadvantage of this kind of platform. Secondly, we have this FPGA plus DSP architecture, which also has highly customizable hardware and abundant peripherals from the DSP. However, the hardware design is complicated and the chip-to-chip communication might be needed. Also, it requires RTL design knowledge. Thirdly, we have this system-on-chip architecture, which provides simple one-chip solution with highly customizable hardware. Also, it can include abundant peripherals. This platform also requires register transfer level design knowledge, and also the logic resources on chip may be limited when compared with the first two architectures. Then finally, we have these third-party solutions like some of the products provided by National Instrument. When compared with the first three architectures, the third one used the third-party software for development, where the first three architectures use the native toolchains from the chip manufacturers. A high-level graphic development tool provided by the third-party company is very easy to learn, and there's no need for RTL design knowledge. However, the controller hardware is not customizable, and the performance of the system may be limited by the third-party development software. So in our application, we selected the Zinc 7000 system on chip from Xilinx. This SoC integrates dual-core ARM Cortex-A9 based processing system designated as PS, and the 28-nanometer Xilinx programmable logic designated as PL in a single device. And for design simplicity, we were using the PicoZ sound board for the controller design. It is worth pointing out that the 7Z015 variant of the PicoZ is not the most powerful option. The main reason we use this variant rather than more powerful variant is that more powerful and faster device can only support 1.8 or 2.5 volt I/O voltage. Low I/O voltage lower I/O pin voltage level means lower noise immunity. In power electronics application, especially with faster switching wide bandgap silicon carbide devices, this might be a big concern. Therefore, we selected this variant, which can support 3.3 volt I/O voltage. Now, here's an overview of the SoC design toolchain. So here are several of here are the softwares we will be using for development this platform. So first we have this Vivado high-level synthesis software. This is for designing FPGA IP core using high-level language like C or C++. And then we have this system generator for DSP, which is a MATLAB Simulink toolbox in which block diagram-based FPGA design can be executed. And then we have this Xilinx Vivado, which is used for system level synthesis and the implementation of the FPGA PL design. And finally, we have the Xilinx SDK, which we will be using this to program the ARM core PS of the Zinc SoC. It is worth noting that other FPGA manufacturers will also have similar toolchain for the same purpose. And in later slides, we will dive deep into this toolchain. Moreover, as mentioned before, since the SoC has two parts on one chip, like one for PL and one for PS, there is a need to have a very high performance interconnection interface in between them. So Zinc 7 SoC has 3 XC4 based interface protocol between the PL and PS. So first we have the XC4 Lite, which is a lightweight single transaction memory mapped interface. It is very easy to implement and use. Then we have XC4, which is also a memory mapped interface, but it can allow a burst of the burst transaction up to 256 data. And lastly, we have XC4 String, which is the most high performance variant of the interface, and it removes the requirement for address altogether. But this one is the most difficult to implement. Now let's look at our detailed design methodology. So here is a more detailed design flowchart for this platform. So as you can see, like for any power electronics prototyping or project, the very first step is to do simulations in environments like Plex. And in the Plex, usually we can first select our topology and the device and size the passive component, and also finalize the sensor selection. In the meantime, on the software side, we will finalize our controller structure, and also we can implement our control design in a discrete manner, like in high-level language. So in this, we can run a preliminary round of validation in pure software environment. So the next step is try to implement the control algorithm in the actual controller hardware. So for this Zinc 7000 SoC platform, the very first decision we need to make is that whether we want to implement particular algorithm in the PS or PL. So if we want to implement some algorithm or controller in the PS part, that would be easy because we already have a prototype, a working prototype C code from the simulation. Basically, we can directly copy and paste them into the Xilinx SDK because the ARM core is programmed with C language. However, if we want to implement some algorithm on the PL side, the process is slightly more complicated. So to make the life easier, we selected to use the Vivado high-level synthesis because it can help us to convert our C code into the RTL design. So the first step is we need to adapting our code style for the HLS, and then we can add directives for timing and the resource usage optimization. And the final step is to run a C synthesis and export our RTL design. So once we have our HLS design, the next step is to actually run a second round validation. So to do that, we can put all our design into this system generator for DSP environment. So in this toolbox, we can export our HLS design, and also we can include some of the HDL source files like Verilog or VHDL file into the same environment. And moreover, we can link our whole stage modeled in Plex with this toolbox so that we can have a code simulation for final round of verification. And after this final round of verification, we can export all our design into the Xilinx Vivado environment. And then in this software, we will run system level RTL synthesis and the bit stream generation. And after the bit stream generation, this concludes the development for the PL side. And then once the PL design is finalized, we can export that to the SDK environment, to generate proper API driver, and then we can start our PS design in the Xilinx SDK environment. So as we mentioned, so here's a comparison between the PL and PS. So the PS CPU is versatile and easy to program using high-level language. However, the PS sequential nature means the absolute performance, i.e. the algorithm execution time for a specific task is no match to the PL. Although there are high-level synthesis tools to simplify FPGA's design process, it is still more complicated than the PS design. Also, the hardware resource of the FPGA would limit how many algorithms can be executed concurrently. Resource utilization and the clock speed are trade-offs in the PL design. If the resource utilization is way too high, there is less placing and routing flexibility, resulting in slower clock speed. With techniques like loop unrolling, loop merge, loop flattening, and pipelining, and the resource sharing, FPGA clock speed and latency can be improved. With the help of tools like HLS, those optimization techniques can be easily applied using corresponding directives. Whereas using conventional FPGA design method, the exploration of the design space might not be sufficiently rigorous. And here's an example code snippet in the HLS. So as we can see, apart from the normal, the conventional C code for the algorithm here, we can add these pragma directives for different optimization goals. I mean, here this directive is used to select DSP core to synthesize the summer for the adder for the summation operation. Also, some of the coding style can be optimized for the HLS, like shown here, because in written this operation in 2 lines can basically tells the HLS to just synthesize one multiplier and use that sequentially to save on the resource utilization rather than compare with the first variant. Because the first variant, the HLS will be interpreted as like it needs to synthesize actually 2 multipliers. And here's an co-simulation setup in Simulink environment between the system generator for DSP and the flags. So as you can see, the blocks with the blue background are the blocks from the system generator for DSP toolbox, while the block with the yellow background are from the flags block set. And there's also configuration menus from the system generator in which we can configure our target devices and the clock speed. The gateway blocks defines the boundary of the FPGA design. And we can also include some of the native Simulink blocks here. And for power electronics application, I think the co-simulation is a better verification method compared with the traditional test bench method. And here's a more detailed on our rapid design verification. As we mentioned before, in the MATLAB Simulink environment, we can include our text block set to represent our power stage. And in the system generator environment, we can import our HLS design and also our HDL files to run a co-simulation between those 2 environments. And then after the co-simulation, we can then export our project, our design into the Nevada environment, and then we can synthesize it and finally download it to the FPGA control board. Now let's look at one of our design examples. This one is for an active power filter. So here's an active APF system overview. So basically, we have a nonlinear load here, and here's the grid, and we have a shunt-based active power filter, which can compensate for the nonlinear current required by our nonlinear load. And we utilize the interleaving topology enables the reduction of the passive component sizes of the LCL filter here. And the developed active power filter is rated for 125 kVA operation, and it can compensate up to 51st order of harmonic with effective switching frequency of 300 kilohertz. And here's the system parameters for our APF system. So here's the controller structure overview for the APF. So as we can see, the current controller for the APF is a hybrid combination of multiple resonant and plug-in repetitive compensator represented here. Moreover, we have the sub-phase balancing control after this main current control, because since we have the interleaving topology. The sampling frequency for the whole control system is 100 kilohertz. And as you can see, in total, we have 15 quantities needed to be sampled at this high frequency. And for more details of the controller design, you can refer to our published paper here. And here's the digital system design for our active power filter. So as you can see, all the control algorithms are, apart from the subphase current balancing, are assigned to the PS side here. And while the ADC interface PWM generation, the subphase current balancing are assigned to the PL side. And we use XC4 Lite protocol for data transmission between the PL and PS. And the execution time will be discussed in later slides. So As we mentioned before, the very first decision making is to whether implement some algorithm in PL or PS. For the active power filter, the controller is set to be iterating at 100 kilohertz. The less computation intense controller structure coupled with this relatively slow iteration speed makes it possible to implement most of the control algorithm in PS. Also, the parameters fine-tuning during the experiment could be faster if the controller are implemented in the PS. The exception is the sub-phase current balancing control algorithm. The reason to assign the sub-phase current balancing in the PL are twofold. First, the results of the external ADCICs are obtained in the PL side, which means the XC4 interface is needed to transfer the data to the controller on the PL side. The most basic XC4 light interface is suitable for this single-shot small data transmission with low overhead requirement. However, if the sub-phase current balancing control is implemented in the PS, then there will be 108 bits of additional data needed to be transferred from PL to PS in each control period. This would significantly increase the execution time, considering the utilization of the XC4 light bus and compromise the digital control performance. Ideally, the nice subphase current balancing controller for each subphase should be running concurrently to reduce the latency. The parallelism nature of the FPGA makes the PL very suitable for this kind of task. Now here's the XC interface implementation for the active power filter. So on the left block here, we have our processing system. And then on the right, we have our controller block. And we use the XC interconnect block here to connect those two together for the data transmission. And in total, 72 bits of ADC data are transmitted from the PL to PS at 100 kilohertz rate. And in total of 30 bits of modulation index data are transmitted from the PS to PL at the same rate. Here's the analysis of our controller. So on the left, we have our the response of our compensated open loop, and which includes the nonlinearity in real hardware implementation, like the digital delay, the sampling by the digital controller, and also the PWM process. As we can see, a gain margin of 9.3 dB and a phase margin of approximately 50 dB are achieved despite the high LCL resonance peak. On the right, the converter admittance YD, that is the current over grid voltage, is shown above, and it achieves passivity up to 16 kilohertz. The passive admittance guarantees damping of any resonance caused by the uncertain grid impedance in the corresponding frequency range. And for more detail on the controller analysis and the passive passivity theory, you can refer to our published paper here. And here's the experimental result. So on the left, is the waveform of the steady state operation. And we have the active power filter current here, and also the nonlinear load current shown here, and also the very clean grid voltage and grid current. This active power filter is designed for a chiller, which has a diode bridge as the front end. Therefore, the nonlinear load used in this experiment is a diode bridge, thus this very distorted load current shape. On the right, we have the FFT results for the nonlinear load and the for the nonlinear load current and the grid current. So as we can see, for a load current of 36.7 Ph.D, the active power filter achieves 2.35% Ph.D in grid current. The harmonic current requested by the nonlinear load is supplied by the active power filter instead of the grid. And up to 51st order of harmonics are compensated. Now, let's look at the execution time and our resource utilization. So, on the left, as you can see, the total execution time of our digital system is 6.4 microseconds, and the most time intensive task is the main control loop and the ADC process. The delay caused by the data transfer between the PS and PL is not very significant. The PL to PS and the PS to PL communication is 1.14 microseconds in total. So as you can see that this ADS7685 IC chip is in charge of the sampling of the grid voltage, grid current, while the MAX 1304 is in charge of the sampling of the all 9 subphase current. So since the ADC results of the subphase current won't be needed near the end of our control period, we can put those two ADC conversions in parallel with each other to save up some significant execution times. When designing an FPGA-based embedded system, 2 key performance indicators are clock speed and resource utilization. The FPGA clock speed achieved here is 200 megahertz. And according to a timing analysis, the slowest path still have 0.13 nanoseconds left with no hold violation. On the right is the resource utilization report. The utilization of all the resources is quite low since most of the computation burden is on the PS side. The most utilized resource is the IOP. This is due to the large number of gating signals and also the external ADC ICs. Okay, now let's look at our second design example. This is a high bandwidth multiemulator. So a brief introduction. Multiemulator is a power hardware in the loop devices which can mimic the terminal electrical characteristics of a real motor. But basically, we can use the multiemulator to test our inverter on the test and also validate our new motor design. So on the left, we have the overview of our proposed multiemulator. So first we have the inverter on the test, and then the multiemulator would sample the output PWM voltage by the IUT. And then the embedded motor model would calculate the current which should exist in a real motor. And the high performance MPC-based controller would regulate the current through the inductor to follow this current reference. And on the right, we have the detailed topology of the setup. As you can see, simple L filtering network and the 2-level VSI topology are selected in this application. High performance current controller and the novel modulation strategy are key components to this high bandwidth multiemulator. Model predictive based control structure is selected for its good dynamic response. And the computation burden of the MPC and the motor model is relieved by the powerful FPGA. And here's the system parameters for our multi-emulator system. Now let's look at the multi-emulator controller. So as we mentioned before, this is a hybrid model predictive controller, and the control is happening at controller is running in ADC stationary frame. As we mentioned before, the hybrid controller is highly integrated with our newly proposed PWM strategy. And here's how the output of the duty cycle from the model predictive controller can affects our modulation strategy. And for more detail regarding this novel modulation strategies, you can refer to our published paper. Now, here's the digital system for the multi-emulator. So, as you can see, online motor model, ADC interface, and the PWM generation, and all the controller are assigned to the PL side of the SoC. On the other hand, the ARM core processing system oversees the data logging over CAN or Ethernet interface. This way, the data logging is running completely in parallel with the control algorithm. The function blocks in the PL can be divided into two categories. The online motor model and the controllers are essentially computation cores. While the ADC interface and the PWM generation are essentially sequential logic blocks. And here's our detailed execution time. So, as we mentioned before, as we can see here, the iteration speed of the multi-emulator digital system is much higher than that in the active power filter application. So, because in here we set to iterate the motor model at 1 megahertz, and the controller is iterating at 400 kilohertz. For such high requirement, there's no way we can achieve this on the PS side. So that's the reason we put all our algorithm and the controller on the PL side. And the PL system can be divided into two subsystems according to the iteration speed. So first we have the 1 megahertz subsystem, which contains our motor model and our resolver emulator. The second one is the 400 kilohertz subsystem, consisting of the model predictive controller, ADC, and the PWM generation. Those two subsystems are running in parallel with each other. So the computation course, like the motor model and resolver computation and the hybrid MPC, are designed in HLS using C++. And to save logic resources, fixed point implementation is preferred over floating point. Xilinx HLS provides a special fixed point number structure for the AP-fix to simplify the fixed point design. On the other hand, ADC and DAC interface can be easily designed with HDL language or system generator for DSP. So now let's look at the PL side implementation. So when the PL design is finalized, the design is exported to the SDK for PS design. The ARM core oversees communication with clock speed of 667 megahertz. The Ethernet communication between the PS and the PC laptop happens every 5 milliseconds. and the controller and motor model are generating data at 400 kilohertz or 1 megahertz. So how to move the data between PL and PS efficiently is crucial to our system performance. So here's the XC interface implementation for the multiemulator. So as we mentioned before, so unlike the system for active power filter, the system in the active power filter is a synchronous system because all the function blocks are running at 100 kilohertz frequency. But in here, we mentioned before, in here we have a asynchronous system here because we have multiple iteration speed for different blocks. So that means the data is generating at a different rate than we can dump it to the PC laptop. So to address this issue, we actually used a block memory here. So we use a block memory here as a buffer. So this is a dual port block memory, and we use one port to write the data from the controller, shown here, the port B, and then we use another port A for reading the data to the PS core. So the buffer in the block memory is cleared every time the Ethernet transaction happens.
So Yukun, we did have a question.
Mm-hmm.
And the question is, can you explain how the model in Simulink is embedded to the FPGA?
Yes, so the model so basically I can go back to slides. So here's the the model in the system generator for DSP, the model shown here. To export that to the rebuttal environment for the system synthesis, we can double-click this configuration menu, and it will show you the export options so that you can package all this design into an IP core, and then you can directly use this IP core in the Xilinx rebuttal software so that you can add that into your design.
Okay. Good. I'll make sure that answers the question. And there was another comment that one of the attendees was kind of expecting more about how the system was modeled rather than presenting a lot of results. And my response was that the emphasis here is actually on the process of implementing the FPGA programming. And yes. I'd just like you to comment. Yeah.
Yes. So for the system design on the controller side of things, we pretty much you can refer to our published paper, and in the last slide I will show a reference list, because in the published paper we have a very detailed discussion of how we model our system and how we chose our controller structure there.
Good, thank you.
Mm-hmm. So now here's the multi-emulator controller analysis. So equipment system model is shown above, and also we have the transfer functions of our compensated open loop and our admittance. It is worth noting that in the plant model shown here includes the parasitic resistance of the inductor, while the MPC is designed ignoring this resistance. Additional unmodeled dynamics may arise due to the nonlinearity of the circuit component and the sensing and the signal conditioning of the sensing and the signal conditioning circuit. To account for the unmodeled dynamic, an integral compensation with gain Ki is added in parallel with the our model predictive controller. A zero-order hold is used to model the modulator, and any variation of the DC bus voltage of the IUT and any other external disturbance is represented by the VB. And here's the and then on the left we have the open response of our system, and on the right we have the admittance response of our system. So the response is drawn with two different persistent resistance value of 20 milliohm and 100 milliohm. The current control bandwidth of 20 kilohertz remain unaffected for the variation of the resistance. And considering the current control bandwidth of the IUT, the switching at 10 kilohertz is designed to be less than 2 kilohertz. The stability of the whole emulation testbed is therefore ensured by the large difference in ME and IUT current control bandwidth. Moreover, high disturbance rejection capability of larger than 25 dB is achieved over the entire frequency range with larger than 50 dB attenuation up to hundreds of hertz. And here's the experimental result and the FFT analysis. So we have 4 set points for our multiemulator with 2 current set point and 2 fundamental frequency set point. And on the top subplot here, we display the current feedback and the current reference. And then on the bottom 2 plots, we run a FFT analysis of the waveform. So as we can see, the current feedback matches pretty well with the current reference. And then also in the FFT analysis, the peaks in current feedback matches pretty well with the peaks in current reference, which validates our theoretical analysis of 20 kilohertz switching of 20 kilohertz control bandwidth. Moreover, the average current error of the system doesn't increase with the amplitude of our fundamental frequency current. Therefore, it is safe to say even at higher fundamental frequency current level, the switching ripple current tracking capability can be ensured.
Yukun, we had another question. Based on the control goals of the motor emulator, how did we decide on the filtering and sampling strategies for phase current and the DC voltage?
So because in this application, we target to emulate the very high frequency switching ripple current. Therefore, on the current sensor part, we selected a very high bandwidth current sensor of up to 1 megahertz bandwidth, and so therefore we basically have minimal added filtering effect on our digital circuit side, because we actually want that high frequency noise, high frequency current to be sampled by our system. And on the DC, on the voltage sensing side, because we need to sample the PWM voltage for the input of our motor model. So this process is done in 2 steps. So we have a dedicated circuit to sample the logic level of the PWM voltage. And then we have another conventional low bandwidth current sensor to sample the actual voltage level of our DC bus. And then by multiplying the logic level with the sampled voltage level of the DC bus, then we can reconstruct our PWM voltage. So basically we have like a 2-step process here for the voltage sampling.
And are some of those details in the reference paper
Yes, yeah.
Okay, thank you. And yeah, those, just to clarify to everyone, those reference papers will be included in one of the last slides.
So here's the timing performance and the resource utilization. So we also achieved the 200 megahertz clock speed for this application, and there's 1.0717 nanoseconds slack, and there's no hold violation. And the I/O pins and the DSP core are utilized at 51 and 55% respectively. The consumption is due to the various peripheral circuits like ADC and DAC needed for sensing and resolving innovation. The high utilization of the DSP core is majorly due to the intensive computation of the model predictive control and the motor model. And among the 65% utilize the VRAM resource, that's the block memory. Most are consumed by the integrated logic analyzer for debugging purposes. Once the development is finished, the VRAM space will be freed up for other use, like integrating more accurate and complicated FEA-based motor model. To conclude, the proposed method utilizes the high-level synthesis tool and the Simulink code generation block set to minimize the need for HDL programming during the system design and expedite the verification process, while not compromising the FPGA platform performance. High FPGA clock speed of 200 megahertz and low control latency are achieved with reasonable resource consumption. The two examples have different controller structure and the control period requirement, which introduce differences in the implemented digital system structure. The experimental result of two examples demonstrates the effectiveness of the proposed methodology based on the two key performance indicators of clock speed and resource utilization for an FPGA-based embedded system. And here's the reference I mentioned earlier. And also this work is sponsored by Power America Institute. And yeah, that will go. Thank you very much.
Thank you, Yukun. So there's your email. Go back to the reference slide if you don't mind, because I know some people will want to take a look at that. And as a reminder, this is recorded, so we'll make that available later and let you guys know when it's, let attendees know when it's available. But we got a question here. Do you expect commercial off-the-shelf HIL simulation platforms like Typhoon or DSpace to be able to do similar tasks like you did in the motor emulator?
Because our for our multiemulator, like, is a power hardware in the loop setup, but like some of the Typhoon's product is like signal level hardware in the loop, so we can actually provide a more realistic results by using our setup here.
And so I guess a follow-on question to that would be, I mean, this is a lot of effort to generate your results for, you know, higher accuracy. Is it worth it?
Yeah, I think so. Like, especially when you are considering the validation of the inverter on the test, this switching frequency level of emulation result I think can actually helps the inverter design and also maybe also impact the motor design. But like on a vehicle level from a vehicle level point of view, this switching ripple current might not be that important.
Okay. Okay. Well, a follow-up question to that. During the FPGA development, did you use any IP blocks from Xilinx that helped?
Yes. So Xilinx, they provided some IP. They have some embedded IP blocks, but I mainly use them for the XC interface. For our for our control algorithm, we design our IP from scratch up.
Okay. Okay. And there's a question here as well about calculations in the number format. Did we use double or single precision floating point number?
No, we like in the PS side we are using I think it's single accuracy there. But like in the PL side, we are actually using fixed point operation.
Okay. Okay. Good. I think that answered those two questions. Let me ask you a question as well, and it's one that I had asked you earlier. You know, this is a lot of work to develop a different process on programming in FPGA. And you explained to me briefly the current process. Could you talk a little bit, I mean, the difference between what you've done here and what the typical programming process is and some of the benefits?
Yes. So the typical way, a more traditional way to do this is that you basically design all your control blocks or your algorithms in using hardware descriptive language like Verilog or VHDL. So basically, you need to write your motor model or your controller using this very lower level language. This can be quite cumbersome and time consuming. And once you finished your design, you need also to write a test bench file to actually verify your design. This whole process can be quite complicated, and it usually may require like a small team to execute this whole process. But like with the help of all these higher level development tools, this process can be simplified, and this whole process can be reduced to a one-man job. Yeah.
Thank you. Yeah, and I think that's, in my mind, that's one of the most powerful, verifications for the work that you've done here. And this was all part of your PhD dissertation.
Yes.
And just briefly, what are you doing now that you've graduated?
So I graduated like in May this year, in June this year, and I will be joining Lucid Motors in September, in this July. I will be working on the power electronics softwares there.
Okay. Well, I don't see any other questions in the chat, and we really appreciate everyone who was able to join. We do have another webinar next month, which will be, Terry, can you unmute and remind me when our next webinar is?
Well, you put me on the spot here. Hold on a second. Yeah, it is going to be on Wednesday, July 21st. And yeah, and the topic is resilient networked microgrids energy management system. Okay.
Thank you. And we'll send a note out, to all the channels that we've used before to let people know. So Yukun, thank you very much. And thank you to everyone who's joined us today. We will end the webinar.